Okay, Jai Hind everyone. Today I am going to discuss the basic content of a brief description of lexical analyzer part. And lexical analyzer generator is basically used for generating the lexical analyzer, in which we have to take source program as input and generate a sequence of tokens, which is a meaningful pattern of the particular program, which we process for the next particular phases. So it is very important. The role of lexical analyzer generator is very important for the whole particular parsing process. So firstly, we have to aware about why this lexical analyzer is needed. So here 3 points is given. One, simplifies the design of the compiler, because if you are directly input the source program to the syntax analyzer, then if you are going to analyze the syntactic specification of the program, it would be little tough to analyze that part directly, because the conversion of source program into syntactic specification of program is little bit tough. So what we are doing, we have to generate a particular lexical analysis page by which we have to scan the particular input or convert it into the different tokens, Those tokens will easily syntactically generated. So it is very easy. So LL1 or LR1 parsing with one token look ahead would not be possible. Multiple characters tokens to match. Second, provides efficient implementation. So whenever we have generate this lexical analysis, we have to break the particular source program into tokens. Tokens are very easy pattern. Tokens are very easy pattern. For those patterns, we have to process easily for the next particular phases. And buffering methods are used for scanning the input. The third thing is improves portability. Basically, we are just eliminating the things which is not required for the implementation of the particular compilation process. So those particular part is removed from the given input. So lexical analyzer is only needed for that, because we are using this scanner. Why? So that syntactic specification of the program would be easily executable. Okay, so that is the need for lexical analyzer. If you are seeing the interaction of lexical analyzer with the parser, so what is the role? Because this is the part of role. The role of lexical analyzer is only to receive the tokens whenever required. Whenever a parser is demands token, at that time lexical analyzer will provide the token to parser, so that the next phase process will be executed. So if you are seeing the role of lexical analyzer only to provide the particular input for the parser, this is the role. So source program is converted into tokens, and that tokens, if you have seen, that tokens will be taking as input for the parser. There are errors also. Maybe you are implementing that lexical analyzer and maybe error is there. If error is there, definitely you have to use some error handling process. Symbol table every time defined for what? Because every time lexical analyzer you have specified some tokens, you have defined some new variables, you have defined some new inputs, some new numeric values. Okay, at that time symbol table will store all the particular thing. So this is the need of lexical analyzer. Role. Then attributes of tokens. So if you are finding the tokens, so basically tokens are identifiers and numbers, then operators, either it is relational, binary operator you can take, and the most important is basically your identifiers. So these are the basically tokens. Okay, these are tokens, numbers, identifiers, relational operators, and keywords. Here no keywords are used, because we have taken a simple statement, that is a mathematical expression, y equals to 31 plus 28 into x. If you are seeing, lexical analyzer will convert it into different tokens. By using these tokens, we can easily process these tokens by parser, because parsers generate parse tree. In parse tree, we have to position the particular operators or different variables or numbers, where the place of these particular things in parse tree, we can easily situate all these things. So if you are taking y equals to 31 plus 28 into x, so y is what? It is an identifier, it is a variable. Equals to, it is an operator that is fixed, because equals to operator unique, meaning it contains. 31, it is a number. So you have see here this particular attribute name and attribute value, that both things are given. Then again operator is there, attribute value column is blank because operator is unique. Then again number is 28, then star is different operator, and ID is also a variable. So if you are seeing the basic tokens are identifiers, variables, or identifiers, numbers, operators, and another one token is keyword. So these are the attributes of tokens that is demanded by the parser to generate the parse tree. Now, three terms are very important, how we can differentiate tokens, patterns, and lexemes. So if you are talking about tokens, patterns, and lexeme, so token is a common thing which is derived by attribute value and attribute name and attribute value. These two things contain token, like ID comma Y. Okay, this is basically your token. If you are talking about lexeme, lexeme are a specific token. If you are talking about Y, Y is an identifier. So whenever you have to convert the generalized token into a specific value which you are going to take as input, this particular value is called basically lexeme. So Y is lexeme, capital A is lexeme, plus is lexeme, less than is lexeme. So these are the lexemes. And the patterns for particular regular expression which is used for deriving any particular string, that is called pattern. So if you are talking about the pattern for identifier that is used for C programming is later or later and later or digit closer. Okay, again I will be right, later. So starting with later or underscore and then later by digit closer. So this is the pattern for the all identifiers. If you are putting any value, if you are putting simple A, it would generate a lexeme capital A. And if you are talking about token, it is identifier of capital A value. So these three terms is very important because we are using these patterns for deriving the string for lexical analyzer generator. So it is very important to understand. So these are basic descriptions about requirement for lexical analyzer generator. Now a specification of patterns for tokens. So an alphabet summation. So summation is what? Summation is basically, if you are talking about finite automata, it is collection of input symbols. That is basically summation. Then a string. A string is a finite sequence of symbol from summation. Summation, you can take a specific part from summation. Then mod of s denote the length of a string. You can define how many length, 4, 5, 6, 2, 1, whatever required for your particular processing. Then epsilon denote the empty string. We are using epsilon which have empty length. There is nothing available, but we are using that because a significant use of this epsilon is there. Then a language is a specific set of string over some fixed alphabet summation. What we are talking about language which is accepted by a particular regular expression, or regular expression is also a language which is accepted by a particular finite automata, that is basically called language, and it is set of summation. So these are tokens because tokens is what it is accepted language for the lexical analyzer that would be creating an output, and we are using regular grammars and regular expressions for deriving it. Then the concatenation of two string x and y is also denoted by xy. So concatenation is also we can take. So concatenation is S0 equals to summation. These are some abbreviations which is used by this particular problem. So we can use any of the abbreviation, but this is given only the concatenation is also a particular string. Two strings concatenation is also a string. So we can derive all the regular expressions. So this is a specification of patterns for tokens, how a string operation we can take. Then a specification of language operations. So union, concatenation, exponentiation, clean closure. Clean closure means it include epsilon. Positive closure, it remove epsilon, means at least the minimum length is 1. So these are the different operations which will applied with the particular regular expression, that is the language for given grammar. Now the important specification of patterns for tokens. How we can find the tokens? The pattern is defined in terms of regular expression, and we all are aware because we have already discussed in different lectures in our class also that specifically we require finite automata to generate this lexical analyzer, and regular expression is the best suitable language which is accepted by finite automata, and that finite automata is derived as lexical analyzer. So if you are talking about regular expression, then what? Epsilon is a regular expression. Every empty string is a regular expression. Denoted language epsilon means only epsilon is accepted in that language. So regular expression means the accepted language by the finite automata. Then A belongs, if any particular one length terminal is there, then it is also a regular expression. Then again, if two regular expressions are there, means some epsilon is there or A belongs to summation is there, okay. Then if two regular expressions are there, then if we are making union of these two regular expressions, we are getting again as a result regular expression, okay. So if you are using this two regular expression, and if you are applying a union operation on these two regular expression, definitely we are getting the resulting regular expression also. Similarly, concatenation operation is also generate regular expression for the two inputs. Then closure is also a regular expression of a particular regular expression. If regular expression is given and you have to take a, you have derived a closure for that, definitely it is also a regular expression. These are the characteristic of regular expression. Why we are studying this? Because for lexical analyzer generator it is required. Then bracket of R is a regular expression denoting LR, like if A is the symbol and if you are denoting is like that, then if in bracket any particular sequence, like if I am writing this A by B closure, so this all is regular expression. If you are breaking it, A is alone, then B is alone, then their union is there, then the union of these is performing as closure operation. These all are the regular expression starting from a small a, small b individual to closure of this particular expression. So a language defined by a regular expression is called a regular set. So whatever language defined by regular expression is called a regular set. And if I am saying for lexical analyzer generator, it is a particular input, it is a particular output for the lexical analyzer, because tokens is represented in the form of regular expression. Whenever we are going to design a lexical analyzer, a machine where we have to take input as a source program and generating the output as a tokens, then definitely what we have to do, we have to generate different regular expressions for different tokens, and we have to connect all these particular machines which is separately designed, and then we are generating a lexical analyzer generator which will take source program as input, and whatever source program sentence has been it extract the particular token by using that machine, and separately that token will be discovered by the lexical analyzer, which may be given to the input for the parser. Now we are using regular definition. So if you are seeing regular definition, it is derived in the form of D1 R1. That is given D1 and R1. R1 is what? It is a regular expression, and D1 is a some distinct name, some variable name that is used for deriving this. So this is called auxiliary definition. If you are talking about lexical analyzer generator, firstly we have to take input as generate a lex using a lex compiler, and by using a lex compiler we have to generate a lexical analyzer, and after that lexical analyzer we have to given the source language with input, and we are getting the lexical analyzer generator. So this is the whole process. In that, when you are using lex compiler, it contains two parts. One is regular definition, second one is translation rule. So if you are seeing that this regular definition is basically translation rules. D1 equals to R1, like if I am using a particular variable, A produces later by digit closure, if I am deriving that. So this is basically that distinct name which contains this regular expression. This is the regular expression for identifier. So whatever identifier you are going to extract that identifier will be generated by this regular expression. And what we are doing, we have to generate a separate machine for that, and that machine will take source program and separately recognize all the particular identifier solely, separately. But when we combine the whole machine, definitely keyword is matching with the identifier, so we have to just checked it out when keyword is find out, because keyword is unique entry, unique token for the particular program. So when keyword is identified, definitely at that time variable is not identified, but before that and after that maybe possibility of variable declaration is there. So here it is given di in Ri can be textually substituted in Ri to obtain an equivalent set of definitions. For example, you have just see letter is derived by capital A by B up to Z, capital letters, then small letters, because you will require to write any letter in terms of that. Then ID, if you are taking, then ID is letter by digit, because identifier is defined. Digit is defined by 0, 1 to 9. All particular digit values are defined by digit. Identifier equals to letter by digit square. I have digit closer that I have given as an example. Okay, so that is given. So one important thing, it is not recursive. It is basically one-time generation whenever you are putting that. If it is recursive, then it would create a lot of complications over there and we would trap in that. So we have to write these regular definition in very specific manner, in very sophisticated manner. Now, notational shorthands. These are some particular notations. If it is required, like R closer, you can write R into R closer, because one length is there, so R is there. R closer you can take, but every time one length is returned, that is R plus. R question mark equals to R by epsilon, means it is epsilon or R single. So these are abbreviation. If you are writing A to Z, this is the expansion of this A, B, C to Z. For example, digit 0 to 9, number of here digit plus, so either digit plus is there or epsilon is there. You can put up anything. Here if this bracket, this question mark, this question mark. So all these abbreviations are used to notate these particular expressions, and we are using these expressions for our calculations. Now, if you are seeing this grammar, it is very important grammar. It is a if else statement. So there is a statement given, it contains if expression, the conditional statement, then a statement, whatever you are going to execute when expression is correct. The next one is if expression, then a statement, if it is false, then else statement, then epsilon. Then expression is derived in the form of term relational operator term. So less than operator, greater than operator, the conditional statement will be given because it is a Boolean thing. Okay, because in terms of Boolean, either it is 0 or 1, then we are getting the answer. So this is the grammar. If you are talking about regular definitions in that, okay, so if produces if is a keyword, this derived if, it is a regular expression, but it is fixed because keyword is fixed in the regular definition. So if derives if is fixed, then is also derived then. There is no change in regular expression because keyword regular expression is unique. Then else is also there. Then if you are talking about relational operator, then relational operator is having a different varieties like less than equals to, less than, greater or equals to. Similarly, if you are talking about ID, it contains these. So for these things, these regular definitions, or you can say that translation rules are used to expand the particular terms which is given in this grammar. Okay, so you have to compare this, and whatever used according to that, you have to put up in that. So this is basically derived. Now, how you can use the transition diagram? It is very important because we have generated the transition diagram for generating the lexical analyzer. The transition diagram is the best flow diagram for designing lexical analysis. For example, if you are designing relational operator, okay, for relational operator, if you are designing the basically transition diagram, then it would be start with 0, then less than is accepted in 1, because less than is not alone, then equals to is 2. Okay, so here 3 conditions are there. Less than equals to accepted on state 2, where return is relational operator less than equals to. So if 2 is accepted, we are getting state 2, definitely it returns relational operator less than equals to. Okay. If you are getting less than, greater than, then third state will be as a accepting state and it would return relational operator not equals to. Definitely, if other is there, means there is less than after suppose A less than B. So B is another identifier. So after less than, other identifier is there. It means the token will change. At that moment, this would return state 4 with return less than. So like that, we have designed this. This is a complete machine which generated relational operator. So if you are inputting any, suppose you are inputting A less than B, definitely it would generate 4. If you are inputting A less than equals to B, it generates state 2. So it generates specifically as a token relational operators because it is designed for only relational operators. Now if you are talking about ID, whatever identifier you have inputted in the given particular statement or given program, definitely you are inputting that firstly letter. Suppose I am taking this A, capital A. Okay, so we input that. So this is letter. After that, letter or digit, because nothing is there, then letter, then less than is other statement or other type of token. So token is changed. So that information would be catered because separate token has been found. So what will happen at that moment? It would generate A and it return get token install ID. Get token is a function where, because this is new variable which is introduced in the program, what will happen? The symbol table will store this particular variable into a place where their installation will be there, their value is generated and that token is taken as an input. So this is the process for transition diagram. If you are taking the code, so this is very simple. Here switch case is used. Why switch case is used? Because keyword is also there and your ID identifier is also there. Then different relational operator is also there. So for that, a simple program that has been designed for generating the tokens for the previous code. So while one switch state, case 0, these are different case, C equals to next char, C equals to blank tab, new line, state equals to 0, Lexeme beginning. So case 0, there will be a taken particular C equals to next char. After that, according to C, else if it is there, then Lexeme beginning, else if C is equals to, this is for operator. Okay, if less than is accepted, 1 is there, equals to like double equals to accepted, 5 is there, else if greater than accepted, 6 is there state. If nothing is extracted as a relational operator, then it would fail and break. Then again case 1. Then the another for identifier is letter C, state 10, else state fail. If letter C is there, letter C means if the current state is letter C, means there will be an identifier. Okay, if identifier is there, then state 10 is there. If not identifier is there, no state is there. Okay, case 10 is letter C, the next state is letter C, state 10, else if is digit. Suppose the expansion is there, suppose we are taking A1, yeah, A11 as a variable. So firstly A is extracted and that A is generated by state 10. Okay, then if you are talking about this diagram, so state 10 is generated. Okay, if A11 is there, so again for this one letter or digit, again 10 state is there, then letter or digit, again 10 is there. After A11, suppose I have defined int A11, okay, int A11, after int, and here is semicolon, suppose, so A11, after that other particular symbol is there, that is semicolon. So what will happen? A11 is accepted at state 11 and it is derived as a identifier and that identifier will be installed into the symbol table if it is not already there. So this is the process. Okay, here now switch start will be taken over there and different cases are there. Which particular case is calling into that case is this particular program in entered. Then again when process is complete, it break and then again it will start with the switch. So this is the process and we can also convert this whole code into 3 address code in which we have to separately analyze all the particular steps and how they execute one by one. We have to study it into intermediate code generation, which is the fourth phase of this particular compilation process. Then important thing, the Lex and Flex scanner generator. Now we are talking about lexical analyzer generator because we have making this background for understanding this. So Lex and its newer caution Flex are scanner generator. Lex and Flex are these are tools which generated the lexical analyzer. Systematically translate regular definition into C source code for efficient scanning. So what they are doing, these regular definitions, okay, these particular tokens will be generated by this Flex and Lex scanner, means for the background of generating those tokens, because it would generate the lexical analyzer generator. So for that, it would generated this. Then generated code is easy to integrate in C application. So we can use C compiler, Turbo C compiler, or any GCC compiler in Unix or Lexical Unix or any Linux platform. So Lex and Flex, these are basically scanner generators. How lexical analyzer will be generated with Lex and Flex? So source program will be taken. What is Lex source program? Lex source program will be containing auxiliary definitions and translation rules. Okay. If you are talking about auxiliary definitions, whatever we are using for regular definitions. So for example, if you are talking about digit and digit equals to 0 to 9. This is basically your regular expression. What is translation rule? Translation rule, like if you are writing begin keyword, it is a regular expression and return 1. It means whenever this regular expression will be deducted, at that moment the machine prompt return 1, means the keyword begin has been discovered by the lexical analysis process. So this is basically translation rules. Translation rule means this is program fragment which would provoked at the moment when this type of regular expression will be discovered. So begin is the regular expression and return 1 basically is what? It is basically the prompt, means it is indication that begin is executed or begin is discovered. So Lex source program contains this auxiliary definition and translation rule. It is called lex.l. Then lex.yy.c. This is basically the lexical analyzer compiler. Then this will be converted, this will be inputted into C compiler. The particular lexical analyzer platform will be generated. Through this lexical analyzer, input stream will be taken and we are getting the sequence of tokens. So this is the process of lexical generator. So in between C compiler is basically Lex or Flex compiler is used to generate for C compiler. Here we are getting the output for that. Okay. So this is the process for lexical analyzer generator. But what is required for that? Then Lex specification, what we have talking already. It contains regular expressions, C declarations, regular expressions, translation rules and user defined auxiliary procedure. Regular definitions are where we have to define D1 produces R1, means whatever regular expressions are derived by using different particular variables. Then translation rules, whenever we are getting how we can identify that this token has been generated for deriving by their program fragment, like if return 1 is there or any return message is there, then which particular regular expression will be derived. Then user defined auxiliary procedure, in between we have to define procedure for generating those particular codes. So translation rule P1 action 1. P1 is regular expression, action that prompt when we are getting this regular expression. So this is Lex specification, we have already talked about that. Now regular expressions in Lex, okay, like match the character, okay, string, okay. So then you have to match any character, then new line, match any character except new line, match beginning of a line. These are different symbols that is used for different character matching. Okay, R1, R2, match R1 when followed by R2. These are programming structures may be used for when you are designing the programs. If you are writing this, you have find that this is basically your translation rules. Okay, 0 to 9 plus. Okay, this is YY text. Basically, when 0 to 9 plus is find out, then YY text is provoked. Next line is there. Then YYLex will be generate the particular regular expression, particular token. Okay, so this is the for second example. Include this will be definition area where integer ch equals to define wd equals to 0 n1 equals to 0. That is the basic part. Then regular definition delimiter equals to /t plus. Okay, because delimiter is what? Because we are using delimiter different places where the /n, then delimiter. So this is the basically translation rules. Whenever we are getting this kind of things, what will be provoked over here? Okay, so that is this, and then finally YYLex will be generated it in terms of n1, wd and ch. These values are generated. Now if you are taking third example, it is very basic example. These are basically regular definitions, because digit you are using, digit contains 0 to 9 values, so we have to define this regular definition so that whenever we are getting 0 to 9, we have to accommodate it here. Then later A to Z, then ID, because we are going to generate the ID. You have seen this. This is basically a program for generating this identifier. Then translation rules are, if digit plus is there, printf number. Okay, if ID is there, identifier. If nothing is there, you have to print other. So this is printed by YY text. This is used for that. Then YYLex is the basic program. So these are the Lex specification which is used for generating the lexical analyzer. Now example fourth, it is having more example because return tokens parser. These are tokens return. You have seen here the translation rule. If return if, then return then, else return then, return else. ID is basically installed, because ID's values every time this particular ID is installed into the system. If it is not, because firstly you have to, whenever you have define any variable, definitely first you have to store in the main memory, then in symbol table. So here symbol table is used for storing that. So these are the then less than, equals to. So this is the complete program where you are getting basically you are getting keywords also, identifiers also, numbers also, and relational operators also. So you have seen that this Lex specification 4 will contains basically a Lex specification is there where 3 parts are defined, that is simply regular definitions, translation rules, and the last one is basically auxiliary procedures. Now design of a lexical analyzer generator. So there are 2 parts is there. Firstly, regular expression have to be taken. Then we have to apply Thompson construction algo. Okay, Thompson construction algo, which convert RE2 regular expression to epsilon move NFA or NFA with epsilon move. After that, we have to apply subset construction algo for converting this NFA into DFA. If further requirement is there, we have to just reduce, or we have to just minimize this DFA if it is required, but this DFA is more than sufficient. So this is the process. So firstly, we have to apply Thompson construction algo, finding NFA with epsilon move. After that, you have to convert this into DFA. So this is the whole process. So firstly, we have to find out NFA. So NFA is a 5 tuple, S summation, then transition, this delta will be there, S0, F. F is the set of final state, S0 is starting state, capital S is a final set of state, summation is set of input terminals, and this one is transition, and that transition is S cross summation. Only NFA and DFA, there is a difference. In NFA, with one input, there is one more than one output states are there, but in DFA, that would be deterministic and only one particular output state for one input transition for input state. So this is the difference. And the DFA is the best designing for generating lexical analyzer. Okay. So if your an NFA can be diagrammatically represented by a label diagram like this. if you are talking about this is directly NFA generated. But if you are applying Thompson construction algo, so like if you are going to design A by B closure for Thompson construction algo, then what you have to do? Firstly design A, then design B, okay, then design A and B closure, okay, this epsilon, this epsilon, this epsilon, this epsilon, then this state is there, then starting state is there, and this one is the complete program of epsilon closure, A by B closure. So if you are applying Thompson construction algo, what it will do? It will do that firstly you have to take this initial A, firstly design for state A, then design for state B, then unionize both, okay, then apply closure for both. So this is the whole diagram for, so this is Thompson construction algo, and it is basically, thank you. So we will cover the rest part in next lecture. Thank you.